Hello, guys. So in this lecture, we want to prove one more theorem on group isomorphisms. In the last lecture, we proved one theorem. So we want to prove one more, and then afterwards, in a separate lecture, we'll look at the kernel of a homomorphism. All right. But we want to start with a definition before we move on to the theorem. It says, let phi be a mapping of a set X onto a set Y, and let A be a subset of X and B a subset of Y. So A is a subset of X, and then B is a subset of Y. Okay. Then of course the image of A and Y, right? Phi will take elements from X to Y. So phi of A here, right, will be the set that is in here, such that if you pick any element in A here, phi maps that, and that falls into the set phi of A. Okay, so that is the definition here. And of course, we are familiar with the set concepts. The set phi of big X here is the range of phi. In other words, if you plug every element in here in phi, you're going to get the range of phi. Okay. Now the inverse of phi here takes elements from Y to X. So phi inverse of B will take elements from B here and map them to elements in big X here, such that if you take any element X in this box, then of course phi of X will be an element in B. Okay. Now, these set theorems, you are familiar with them, but we'll be applying them in the proof that we are going to show in a minute. Okay, so that's why I'm revising them here. So take a look at these this definition and familiarize yourself with them. Okay, good. Okay, so here's a theorem. It has 4 parts, so it's a bit lengthy. So that's what we want to look at. It says that let phi be a homomorphism. We know what that means. Homomorphism of a group G into a group G prime. If E here is the identity element in G, then phi of E is the identity element E prime in G prime. In other words, phi of E is equal to E prime. I'll explain that in a minute. For all A in G and for all N and set of integers, you can always write this. Phi into A to the power N is equal to this, all right? In particular, if you take the inverse, you get the inverse in G prime. Okay. The third part says that if G here is a group, is a subgroup, I should say, a subgroup of G, then phi of H is a subgroup of G prime. And if K prime is a subgroup of G prime, then phi inverse of K prime is a subgroup of G. Okay. Now, what does this all mean? Let me sketch a couple of things here, just so you understand what all this is saying. Okay, so this says that if I have a function phi, this is a homomorphism. It takes elements from the group G to the group G prime. Okay, from G to G prime. Okay, good. Now, since G is a group, of course, it has an identity element. Let's call that E. Okay. And of course, phi here, the function phi will map E here to an element in G prime. Let's call that phi of E. Okay. Now, this element here, right? This element here, phi of E, is in G prime. But the theorem is saying that this element is the same as the identity element in G prime. Okay. So we say that homomorphisms map identities to identities and they map inverses to inverses. Okay, so that is what that means. In other words, if I take the identity here and I apply this map here, which is a homomorphism, if I apply it to E, I'm going to get this element here. Now the element that I get is exactly the identity element in this other set here, in this other group G prime. Okay, so that's what the first one says. The second part says that, for instance, if I have an element A here, well, phi here, this homomorphism will map A to, of course, phi of A, okay, which is an element in G prime. Okay, note that in A here, the identity element in A, the identity element of A in G will be A inverse, right? A to the negative 1, okay? The identity element of this guy here, okay, in G prime is, of course, is phi A, all of that to the power negative 1. You see that? This guy here, the identity, the inverse of phi of A in G prime is given by this. The theorem says that if I take phi, right, if I apply phi to this inverse, for instance, if I'll get phi of A inverse, the theorem says that this is exactly the same as this inverse. In other words, I can take this -1 up here, okay? So, and we are going to do it in general, actually, not just to the -1, see? We're going to prove it for general n, where n is an integer. So basically, that is what the first two are saying. So homomorphisms map identities to identities and inverses to inverses. Okay, let's look at the third part. The third one says that I'm doing the sketches here so that once we start doing the proof, you get to understand what is happening. Okay, and I like to do the sketches. They help you visualize, understand the proof too. Now, if H is a subgroup of G, so it means that H is in here, right? Subgroup of G. Then, of course, when you take this phi of H, you're going to get an element that is here. So phi of H, of course, is in G prime. Okay. So if H is a subgroup of G, this theorem says that phi of H is a subgroup of G prime. Okay. And remember some of the theorems that we looked at in our last lecture, right? How to prove that a subset of a group, right, is a subgroup, okay? I'll remind you of 2 of those theorems because we need that here. So basically to prove that this H is a subgroup, you need to prove 2 things, right? If you use one of the theorems that if A and B are elements in H, then A times B or A star B is also in H. And if A is in H, I will also want to show that A inverse is also in H. Okay, these 2, if you're able to show these 2, then it proves that H here is a subgroup of G. We've seen this already. So we can do that. This one says if H is a subgroup of this, then this is a subgroup. So we want to do the same thing. We want to pick elements in phi of H and show that their product is also in phi of H, and take an element in it and show that the inverse is also in phi of H, okay? Once we've done that, we have shown that phi of H is a subgroup of G prime, okay? So that is the third one. And the fourth one we want to prove is this. If K prime here is a subgroup of J prime. Now K, let's get rid of this. K prime is here, right? K prime is a subgroup of G prime. So K prime, you can consider K prime on this side. Well, the inverse will take elements from G prime from here, right, to here. So this is the action of phi inverse, right? So this will be K prime. Okay, so phi inverse will take elements from K prime to phi inverse of K prime. So you get that. Good. And then if this is a subgroup of this, the theorem says that phi inverse of K prime is also a subgroup of G. Okay. So hopefully you have an understanding of what the theorem is about. Okay. So okay. So these are the 2 theorems that you should keep in mind. We're going to use theorem 3 that we looked at already in one of our lectures. Okay, this is a reminder of it to show that H is a subgroup of G, you have to show that it is non-empty, and that if I pick any two elements in H, the product is also in H. If A is in H, the inverse of A is also in H. Once you show these two conditions, then you have, of course, plus the fact that it's non-empty, then of course you can conclude that it is a subgroup. So keep that in mind. We'll be using this a lot. Well, the other one we've seen before is this. We'll not use this very much. But theorem 4, you can revise it if you want to. Okay, so how do we prove this? Let's prove the first one, that if E is an identity of G, then phi of E is the identity element in E prime. The identity element E prime in G prime. Okay, so basically we want to show that this is true. Okay, good. So let's go ahead. So this is a statement of the theorem. Let G and G prime be groups, and let phi mapping G to G prime be a homomorphism. Okay. Well, remember that we already described what a homomorphism is. Basically, a function is a homomorphism if I do phi A times B, or A action of A on B gives me phi of A, right, times phi of B. All right. Or if I have this, I can write it like that. Okay. So basically that is what it means to be a homomorphism. Okay. Great. Now, so let E here be an element in G, and E prime be the identity, right? We already did this at the identity in G. Let E prime be the identity in G prime. Okay. Now, phi of A, right, is equal to phi of AE, right? Because E is the identity in G, A times E will give me A, right? So this is equal to that. All right. But phi is a homomorphism, so I can spread it. I can rewrite it like that, right? Because it is a homomorphism, I can rewrite it like this. Okay, great. Now, note that phi G prime here is a group. Therefore, every element in G prime has an inverse. Okay, so phi of A, for instance, is an element in G prime, so it definitely has an inverse. So I can multiply this side by the inverse of phi of A, and I can do that for this side. So if I do that on the left hand side, I get this. On the right hand side, I have this. Okay, but of course, phi of A inverse times phi of A will give you the identity, right, in G prime. So that is why we have this. And then phi of A, the identity of that multiplied by phi of A also gives you the identity element phi E prime. But E prime is the identity element. Therefore, if I multiply E prime by any element in G prime, I'm going to get the element back. So of course, this should give me phi of E. You see that? Because it's an identity. So we have shown that E prime actually is equal to phi of E. Okay. So that is what we have proved. So we have shown this, that phi of E is equal to E prime. So basically that's what we wanted to show, that the identity element in G actually maps to the identity element in G prime. So this first one is kind of straightforward. So we'll move on to the second part. Okay, the second part, it is a bit lengthy, right? It's lengthier than the first one. So here we want to show that, basically we want to show that this is true. If I pick an element A, which is in this group, and for every integer, I can always write this. I can always do this. Okay. So that is what I want to prove. And now we want to prove this by induction. So you need to remind yourself of the procedure for mathematical induction, right? So I'll briefly mention that before we go. So this is the procedure for mathematical induction. So we have a statement. We're going to call it, let's say, P of Pn here. Pn is our statement that says that if I take phi into An, this I can write as phi A raised to the power n. Okay, I want to show that this is true. Okay, this is equal to that. So by mathematical induction, the first thing you do is you can show that it is true for instance, when n is 0. Okay, 0 is an integer. Well, when n is 0, it is true because we're going to have phi of a to the power 0. This is, if you like, phi a all raised to the power 0. Well, phi a to the power 0 is 1, which is the identity element for multiplication, the multiplicative identity elements. So basically, this means phi of the identity element is equal to, this is the identity, this guy here is in G prime, right? So to the power 0 will be the identity element in G prime, which is E prime. And we have already proved this in part 1. So n is, of course, true. Then we want to show that it is also true for when n is 1. Well, when n is 1, I'm going to have phi into a to the power 1 and phi of a raised to the power 1. Well, they are equal, clearly, right? So the statement P of 0 is true, P of 1 is also true. Well, by mathematical induction, the next thing you do is that you assume that the statement is true for n is equal to some k, where k is greater than 1 or greater or equal to 1. We've proved 1 already, right? So that means that we are going to assume that this is true. Phi into a raised to the power k is equal to phi of a, everything raised to the power k. Okay, so we're going to assume that this is true. Once you assume that this is true, the next thing is to prove. Now you have to prove that it is true for n equals k plus 1. Prove that it is true for when n is equal to k plus 1. Okay, so basically you want to prove that if this is k plus 1, right, I'll also get k plus 1 at the top here. Okay, so once we have done that, all right, once you have shown that it is also true for n equals k plus 1, then basically you have shown that the statement is true for when n greater or equal to 0 for all positive integers. And then after that, we also do it for the negative integers to show that it is true for all integers. Okay, so that is the idea behind it. So I will skip some of this in the proof because basically this is what the proof is doing. The first part is basically this. The second one is this. The third part by mathematical induction is to assume that the statement is true for when n is equals to k, and then we prove that it is true for n equals k plus 1. Okay, so that is the plan for the proof. Okay, so let Pn be equals to this. As I said, when n is 0, well, this is equal to that. Therefore, it is true because we have already proved this in part 1. Okay, when n is 1, you have this is equal to this, which is true. So this statement again is true for when n is 1. And then you assume that, or you suppose that it is also true for when n is k. By that, we mean that we take it, okay? We take it by mathematical induction. We take that this is true, okay? So when n is k. Well, if it's true, then the next thing is to actually show that it is true for k plus 1, okay? We want to show that it is true for k plus 1. So how do we do that? Phi, so you plug in k plus 1 into the statement, right? You put k plus 1 into it. What do you get? Now, know that a raised to the power k plus 1 is equal to a to the k multiplied by a, right? That is just from basic algebra that we know. Okay, if I plug this into this is what I get. Give me a minute, sorry. So give me just a few minutes. I will get back to you in a bit. Sorry. So we have this, right? So from here to here is straightforward because a to the power k plus 1 is the same as a to the k multiplied by a. Okay. from the fact that phi here is a homomorphism, we can write it like as this. Okay, we can split it into phi a to the power k and then phi of a. All right, so we can actually do that. Then we can also rewrite. Note that k here we said k here is positive. Okay, and by the statement of the induction, this is true. We assume that that is true. So which means I can write phi a to the k as this and multiply by phi of a. Well, this guy to the power k times this guy is the same as phi of a raised to the power k plus 1. Okay, so this is the same as a to the power phi of a to the power k plus 1, which means that the statement is true for k plus when n is k plus 1. Okay, hence p of n here is true for all values of n greater or equal to 0. All right. Okay. So we have proved that it is true. The statement is true for all positive integers. Okay. Question is it true for the negative integers? Okay. So we let how to do that. We let n be equal to negative m, where m is positive. That makes the n here negative, right? Okay. So we let n to be equal to negative m for n positive, and then we know that a to the m raised to the a to the n raised to the power a to the m, well, one is the negative of the other, so it's a to the power 0, which is the identity element, right? So this gives you e. Okay, I've explained that. Okay, good. So now you can take the phi of both sides, all right? Phi of this guy, because phi is a homomorphism, I can split it to get this. Now, phi of e is the identity in J prime, so that is E prime. Okay, we have proved that already. Okay, good. Now, okay, what I've written here is the same as what I'm stating here. Now, because m is positive, this part, we can actually use the statement of the hypothesis, right? The first part that we proved for positive integers. We can apply that here. So this can be written as phi of a all raised to the power m, right? And multiplied by this. So we can actually write this because m is positive, okay? And so if you do that, you're going to have this. A phi into a to the n, phi of a raised to the power m, all is equal to E prime. And then you have phi raised to the power n is equal to E prime times phi of a raised to the power negative m, right? You can multiply the right side here and the right side here by phi of a raised to the power negative m, right? And then you get that. Good. Now, E here is the identity element. So if I multiply by this, I'll get back the same thing, all right? But remember that negative m here is n, okay? Which means phi into a to the power n is equal to phi of a raised to the power n. But remember, n is negative. So we have proved the statement for negative integers, okay? Therefore, the statement P of n here is true for all n, all right? For all n in the set of integers, all right? Now, in particular, if you plug in n is equal to -1, of course, you get this. You can just use, we have proved it for the general case, so we get this for free, right? So a homomorphism will take an inverse. It takes inverses to inverses. Okay, that is what this is showing. Awesome. Okay, now on to the third one. So let me go back here and remind you of what the theorem says, okay? And then we'll prove the third part of it. The third part here, let's see, is here. Okay, this third part says that if H here is a subgroup of G, then phi of big H, right, is a subgroup of G prime. All right, I already explained that. Okay, if H is a subgroup of G, then phi of H is a subgroup of G prime. Okay, and I said that we want to take elements, right? We want to use theorem 3 to take elements in here and to show that if you multiply them, their product is still in phi of H. If you take an element, let's say A here, and you find the inverse is still in phi of H. So basically, we want to use this theorem here, theorem 3, to prove it. Okay. Okay. So let's go to the third part and then prove that. Okay. So here. Okay. So keep in mind phi is taking elements from G to G prime. H is here, it's a subgroup. Of course, phi of H is here. You see, phi of H will be there. Okay. So given this, we want to show that if H here is a subgroup of G, this guy here is a subgroup of G prime. Great. Now, this is given from the theorem. Well, since H here is a subgroup, it's a group, a subgroup is a group, right? It's a subgroup of G. Of course, it contains the identity element. Remember that the identity element is unique, right? Therefore, if H here is a subgroup of G, right, it must contain the identity element. So E, of course, is in H. Now, if I take phi of E, I'm going to get E prime, right? But E prime has to be in phi of H. So E prime here is the identity in G prime, right? In G prime, right? So if I take phi of E, because E is in H here, phi of E prime here has to be in phi of H, okay? That proves that phi of H here is not empty, okay? So the first thing, we know it's not empty. The next is to take two elements, find the product, and also show that the product is an element in phi of H, okay? So we take X and Y in phi of H. Well, what does it mean? For an element to be in phi of H here, it means that there has to be some kind of element here. Let's call it H1, let's say, right? There is some H1 here in H, so that if I take phi of H1, I'm going to get this element. Let's call that X. And if I take phi of, let's say, H2, I'm going to get another element Y. That's what it means to be an element in phi H, okay? So that is what we have here. If X and Y are elements in phi of H, it means that X is equal to phi of H1, small h1, where small h1 is an H, big H, and Y will be this, okay? Good. Now, if I multiply those two elements, of course, X is this and Y is this, so I multiply them out. Phi is a homomorphism, so I can regroup it like this, okay? And I can rewrite this as phi of H, right? H is a subgroup. So if I multiply any two elements in H, I get another element, right? Let's call that small h, which must be in H as well, okay? So X times Y is equal to phi of little h here, okay? Which means that X times Y is an element in phi of H, okay? So this guy is an element in phi of H, phi of H. Well, the next is to show that if I take an element in phi of H, its inverse is also in phi of H, okay? And this will help us to do that. So X inverse here, note here, we already have X is equal to this. So if I take the inverse of that, it's equal to taking the inverse of this, okay? But we have proved, right, in the theorem where we use the mathematical induction, right? We proved that this can be written as that, okay? But H1 raised to the negative 1, that is the inverse of H1 here, exists because H itself is a subgroup. So every element in H has an inverse, okay? So H1 inverse is in H, okay? So that is because of this, because H1 inverse H, which means that, right? Which means that X inverse here has to be an element of phi of H because this guy is in big H, right? So phi of H is a subgroup of G prime, okay? So we have proved the third one, the third theorem, the third part of the theorem, okay? Good. We want to prove the last bit. The last one is here. And then we'll be done with this part, this video. Okay, again, I'll remind you, phi takes elements from G to G prime. Okay. The theorem says that if I have K prime to be a subgroup of G prime, then the inverse function, right? Then phi inverse of K prime. Okay, all of that is also a subgroup in G. Okay, so that is basically what we want to prove. So it's the same approach. If I take two elements in here, well, first of all, I'll show that this guy here is non-empty. And if I take two elements and multiply them, I get an element that is in it. And if I take an element in here, I also show that the inverse is also in it, just like we did for the other one, but now for this set. Okay. Good. So let K1 be a subgroup of G prime. Then we know that G here is a group, therefore E is an element. It has an identity, which is E, and phi of E is equal to E prime, and that has to be in K prime because K prime here is a subgroup of G prime. E prime has to be an element of it. All right, good. So this is a trick that you will see often, right? Since E prime here is an element, belongs to K prime, okay, I can take the phi of both sides and this will still remain the same, or phi inverse. Okay, you see that? So since E prime here is an element in K prime, if I take phi inverse of this, it has to be in the phi inverse of this. Well, phi inverse of E prime is in G prime, so inverse of it will take me back to E. So this is E, right? The identity in G. This has to be in phi inverse of K prime. Okay. So keep that in mind. You'll see that quite often in here. Okay. So we have shown that E, right, the identity element in G here belongs to phi inverse, which means that it is not empty. Okay, so that's the first thing. Phi inverse of K prime is not empty. Then if I take two elements A, B in phi inverse, right? Know that phi inverse is here, right? So any two elements in here are also elements in G, right? Okay, so A and B has to be in G. Well, phi of A and phi of B, of course, they map to here. They map to this side, all right? So phi of A and phi of B must be in K prime, all right? Because A and B are in the inverse of K prime. So phi A, phi B has to be in K prime. Well, remember that K prime here is a subgroup, okay? So if I take any two elements of K prime and multiply them, it will still be in K prime, okay? So if I multiply them out, know that phi is a homomorphism, so I can rewrite it like this. So this quantity here has to be in K prime, okay? That means if I take the inverse, I'm going to get AB belonging to phi inverse of K prime, okay? So if I take two elements in phi inverse and multiply them, the result is still in the phi inverse of K prime. So we have proved the first part. Okay. Now also remember that phi of A here is an element in K prime, but K prime is a subgroup, which means that every element in K prime has an inverse. Therefore, phi of A here has an inverse as well, which must be in K prime. Okay, so phi of A is in K prime means that the inverse must also be in K prime. All right, since it is a subgroup. Well, note from our proof again, the part 2, right, where we use the mathematical induction, that I can rewrite this as that. This is phi into A inverse, right? That must belong to K prime. Okay, well, so I can take the inverse now, right? Or multiply by the inverse of both sides, or take the inverse of this and that. If I do that, I'll get A prime belongs to the phi inverse of K prime, which means that if you take an element in K prime in the inverse, where is it? Yes, so you get A inverse to belong to, what is it? K prime, okay? So we have an element A, which is here. The inverse of that element is also in in phi inverse of K prime. Okay, so taking the fact that phi inverse of K prime is non-empty, the product of two elements is still in it, and the inverse of an element is in it, we can conclude that phi inverse of K prime is a subgroup of G. All right, so that brings us to the end of this theorem. Okay, so we'll end it here, and the next lecture, right, the next video will cover the kernel of a homomorphism. Okay, so that's what we'll be looking at next. Okay, so I will end this one here.